Looking back on things now, it seems so simple, but it must have been hard to swallow the notion that motion is made up of two or more components in different directions. Back then, it was by no means an easy concept, even for scientists to accept. Imagine that. Obviously, dealing with this combination of forces, many scientists experienced a mental block big time. So when Copernicus first suggested that the Earth moved around the Sun, some of the most vehement objections came from those scientists. Their counterargument to his was if the Earth rotated on its axis and moved through space revolving around the Sun, it surely would be impossible for anything movable to remain fixed to the Earth's surface. Geez, if one leaped up in the air, he would come down many yards away, since the earth beneath him would have moved while he was in the air. Well, likewise, they had trouble believing that the moon was affected by the same force as the proverbial apple, simply because if the same force applied to both, the same acceleration would affect both, and both should fall. Well, Galileo showed this wasn't so by pointing out that an object dropped from the top of the mast of a moving ship fell to a point at the base of the mast. In other words, the falling object doesn't fall in the water, even though while moving downward, it must also have participated in the ship's horizontal motion. Actually, Galileo did not try this himself, but he proposed it as what is today called a thought experiment. Even though it was proposed only in thought, it was utterly convincing. You see, ships had sailed the sea for thousands of years, and objects must have been dropped from mast tops during all those years. Yet no seaman had ever reported that the ship had moved out from under the falling object. Never. Then why did some scholars of the 16th and 17th centuries feel so sure that objects could not possess two different motions simultaneously? Apparently, it was because they still possessed the Greek habit of reasoning. What this means is that they reasoned from what seemed valid basic assumptions and did not always feel it necessary to check their conclusions against the real universe. That's why I feel hesitant to call them scientists, and rather refer to them as scholars. For example, the scholars of the 16th century reasoned that a projectile fired from a cannon was potentially subject to motions resulting from two causes. First, the impulse given it by the cannon, and secondly, its natural motion toward the ground. Assuming that an object could not possess two motions simultaneously, one motion would be completed before the second began. In other words, they deduced that the cannonball would travel in a straight line in whatever direction the cannon pointed, until the impulse of the explosion was used up, and it would then at once fall downward in a straight line. Galileo, on the other hand, argued that the projectile traveled onward in a direction in which it left the cannon, and that the cannonball began dropping as soon as it left the cannon's mouth. That is to say, Galileo abandoned Aristotelian notions about motion and was instead taking a totally new approach to the problem. In one experiment he did conduct, Galileo demonstrated, by dropping bodies of different weights from the top of the famous Leaning Tower, that the speed of fall of a heavy object is not proportional to its weight, as Aristotle had claimed. But his attacks on Aristotle made him unpopular with his colleagues, and in 1592 his contract as chair of mathematics at the University of Pisa was not renewed. What a drag! This seems to happen so often to trailblazers who challenge the authorities of their time, doesn't it? Well, in any case, by 1609 he determined the law of falling bodies. As you may guess, what the law says completely contradicts Aristotelian physics. It states that the distance traveled by a falling body is directly proportional to the square of the time it takes to fall. For example, a stone falling for twice as long as another stone will travel 4 times the distance. Or, a ball falling for 3 seconds will travel 9 times the distance traveled by a ball falling for 1 second. On the basis of this law, Galileo reached the conclusion that bodies fall to the surface of the earth at a constant acceleration, and that the force of gravity, which is the cause of all bodies moving downward, is a constant force. In other words, a constant force does not lead to constant speed, but to constant acceleration. Well, in the period before him, people thought that force causes speed. That's what Aristotle believed. Instead, Galileo showed that force causes acceleration. This is also inseparable from his principle of inertia, that a body in motion will continue its motion so long as no factor disturbs that motion, which is, by the way, our topic next Thursday. The law also states that the trajectory of a projectile is a parabola, which means that the object thrown follows the path of a curve called parabola. That's why the law is sometimes called the law of parabolic fall. And he also showed that a cannonball would have the greatest range if the cannon were pointed upward at an angle of 45 degrees to the ground, the validity of which, by the way, was repeatedly demonstrated in the battlefields in numerous subsequent wars. Looking back on